Hello, my name is Yadama. I'm from Composite Materials and Engineering Center at Washington State University. Today I will be presenting our proposed idea of natural fiber reinforced nylon-based composites for under-the-hood automotive applications. It addresses seed concept 2 and 3, buffalo hemp carbon sequestration and hemp-based polymers. I would like to acknowledge my co-PIs Raul Pele Samaniego and Manuel Garcia Perez. The problems that this project will solve are as follows. We know when biomass is used with polymeric materials during processing of it, whether it's injection molded or extruded, is the fact that it generates very high viscosities. And also the processing temperatures could be limited below 200 degrees centigrade because the biomass will start degrading. Additionally, there could be poor compatibility between the biomass and the polymer. But by producing hemp-hurd biochar that we are proposing in this project, we could start addressing the issue of processing at much higher temperatures, about 200 degrees centigrade, and not degrade the biomass. This project would also offer basalt fiber as a substitute for glass fiber for automotive industry that is seeking other alternative materials, especially with recent interruptions in the supply chain and significant increase in cost. This project will also show how to continue to store carbon in products through use of hemp-hurd biochar. So in terms of industry relevance and the needs, this project provides an alternative fiber to glass fiber that has good mechanical and thermal properties, if not better. And basalt fiber, we know, is an excellent candidate for that. The project will also provide an understanding of injection molding and 3D printing with basalt fiber, polyamide, and biochar formulations to produce a thermally stable and lightweight material for under-the-hood automotive applications. In regards to previous work, first I'd like to talk about a CB² supported project in 2019 and 2020 that examined basalt fiber hemp-hurd polypropylene injection molded composites, looked at the effects of formulations, understood the rheological behavior and how it relates to processability, and analyzed preliminary VOC emissions when exposed to high temperatures and UV. I'm going to briefly present the findings of that study. We found that with 30% basalt fiber in the formulation, it can yield composite material that has similar stiffness to glass fiber formulations. And with inclusion of sized basalt fiber and coupling agent, we can achieve also strength properties similar to glass fiber. And inclusion of hemp-hurd reduced the weight of the composite material on average by 4 to 5%. Breakage of basalt fiber was significantly less than glass fiber breakage. And the basalt fiber blends generally yielded lower viscosities at all shear rates when processed. However, the formulations with hemp-hurd exhibited highest viscosity properties. And so at the end, we found that basalt fiber polypropylene could perform as well as glass fiber polypropylene are better, and especially with effective sizing of basalt fiber. When we reviewed the available literature, what we found was that very limited studies done on basalt fiber nylon composite materials. These were done in Eastern Europe and Asia. Generally, the basalt fiber was treated with silane in order to provide a good interaction with polyamide. And there was some work that was done to evaluate polypropylene that was combined with polyamide and basalt fiber. And generally, people found that basalt fiber aligned very well with the flow of the resin, and the aspect ratios were much higher, about 130 when long fibers were used. Additionally, what we found in regards to use of basalt fiber for 3D printing was that it was used with other resins such as PET, PLA, and ABS. However, there was very limited work done on use of basalt fiber with nylon to produce filament for 3D printing. Therefore, we conducted some preliminary work with 3D printing to show that it is possible to process polyamide with biochar and basalt fiber using 3D printing. The figure here shows filaments as well as specimens, tensile coupons that were produced using the two formulations. Both these formulations included basalt fiber and polyamide, but the formulation on the right also included 10% biochar, whereas the formulation on the left did not have any biochar. We examined the specimens that were produced using optical microscopy and found that the blends that had biochar included in it, like the one on the right, had a natural black pigmentation to it. And when we conducted some tensile testing in order to evaluate the Young's modulus, what we found was formulations with basalt fiber included definitely had significantly improved Young's modulus compared to neat polyamide specimens. But however, what we found was with inclusion of only 10% biochar, the Young's modulus tremendously improved, significantly improved compared to the formulation that included 40% by weight basalt fiber. And one of the things that we would like to actually examine further in this study was, why is this increase significant because of inclusion of biochar? Is it helping with the interaction between basalt fiber and polyamide? And if so, how? So the project goals are to study the conditions in which basalt fiber and hemp hurd biochar can be processed with polyamide to produce composites appropriate for under-the-hood automotive applications using injection molding and 3D printing. So why use polyamide? Because it has high mechanical strength, high thermal stability and rigidity, low permeation to organic vapor and liquids, and great oxygen barrier properties. So why do we want to use basalt fiber in this project? There are several strengths outlined here, but some of the important ones are the fact that it has strength and stiffness that is comparable to glass fiber. It has very good resistance to moisture absorption, fire, and wear. And it's a naturally occurring material since it's derived from lava rock, so the end-of-life options could include returning back to soil. Another major advantage over glass fiber is that it consumes less energy during manufacturing. In regards to challenges, there is a lot of variation in the properties of basalt fiber depending upon the region it's derived from, and also the fact that it needs sizing as well, just like glass fiber, for better interaction with polymer systems. So why do we want to use natural fibers, and especially biochar derived from hemp hurd in this project? Some of the strengths of natural fibers are the fact that they have lower density and they're renewable and of low cost. The challenges include higher moisture absorption as well as constraints on processing temperatures, because anything about 200 degrees centigrade would start degrading the biomass. And this is where biochar plays a vital role. Biochar is produced by thermally decomposing biomass such as hemp hurd under oxygen-limited conditions, and typically the temperature could range between 300 degrees centigrade and 1000 degrees. Biochar is nothing but carbon-rich, fine-grained material with increased surface area and could potentially have some functional groups. Since biochar is more thermally stable, it allows us to use higher processing temperatures, and therefore we can process it with polyamide. So the approach we'll take in this project is we'll take hemp hurd and pyrolyze it, and then take the hemp hurd biochar and compound it with basalt fiber and polyamide in an extruder to produce pellets, which will be then used to make filaments for 3D printing, or fed into an injection molding equipment in order to produce composite material for performance evaluation. Hemp hurd biochar will be ground to a particle size of approximately 100 mesh. We'll also make hemp hurd biochar at 3 different processing temperatures, low, medium, and high, and we'll characterize the biochar produced using these 3 processing temperatures for their thermal stability, structure, and composition. This is critical to understand its interaction within the composite with other materials. So once we determine the ideal processing temperature for hemp hurd biochar production, we will use that temperature to produce rest of the biochar using hemp hurd, and use that in making different formulations. That is a combination of the varying proportions of the 3 components: hemp hurd biochar, basalt fiber, and polyamide, as shown here. And then the materials will be compounded using a 16 millimeter extruder and pelletized to a length of 3 to 5 millimeters. For producing filaments, we'll use a capillary rheometer at 220 degrees centigrade, and the filaments that are 1.75 millimeters in diameter will be produced. Then using these filaments, we'll produce 3D printed tensile and impact specimens, and they'll be tested as shown here using the guidelines outlined in the ASTM standards. The pellets will be directly used for injection molding, as I mentioned before, and we will definitely determine the ideal processing parameters to produce specimens without any voids, and we'll produce tensile and impact testing specimens and test them according to the ASTM standards here. We'll also actually produce flexure specimens and test them as well. And the composite structure will be analyzed using microscopy. In regards to the outcomes, the project will deliver proven formulations of hemp hurd biochar, basalt fiber, and polyamide for both injection molding and 3D printing. It will also determine the thermal modification process required to produce a suitable hemp hurd biochar to blend with polyamide and basalt fiber to produce composite materials ideally suited for injection molding and 3D printing. And will determine also the processing parameters for the filament production, which is a critical step towards 3D printing, as well as the processing parameters required to produce specimens or to produce composite materials using injection molding. If we need any additives, that will be determined as well. As for the impacts of the project, it will provide an alternative fiber to glass fiber. Use of hemp hurd in the form of biochar will benefit hemp growing communities. Inclusion of biochar will lighten the composite, provide more fire resistance along with the basalt fiber, provide the common black color in under the hood parts without the need for oil-derived pigments. And if biochar improves the interaction between basalt fiber and polyamide, it will give us an insight into this mechanism as to how biochar is improving this interaction. And finally, the proposed project has a duration of 1 year. We're requesting a total budget of $59,700 to support graduate student and limited time of PIs, pay for materials and lab fee, travel, and 10% IDC. The table here shows the timeline of the project with the corresponding tasks listed next to it. Thank you very much for your attention, and we look forward to answering any of your questions that are presented through the live forms.